Hello, today we're going to talk about composite functions. The difference between composite functions and when we did the last section, algebra functions, is now rather than adding, subtracting, multiplying, or dividing them, we are actually going to put one function into another one as if it were the own x value. So each function is kind of like a machine. And when you put something in, you get something out, but they're not all alike. If you use a different function, even if you put the same thing into it, you're going to get something different out. And so I realize this may be kind of hard for you to see, but just kind of trying to use a little bit of humor to illustrate it. If we've got to change a dressing room here, but one of them is a dog suit machine, you're going to get a very different result than if you use a dressing room that has a human suit machine. And to just kind of illustrate this along the way, we'll click through a few slides. If you put a man into each of these machines, in the one you're going to get a man in a dog suit, but in the other one you get a man in a man suit. Okay, so it's not the same thing, even though we had the same X to put in. Now, you could end up putting a dog into the man suit machine. We might get the same suit, but it's going to look entirely different. Of course, you could possibly put a dog into the man suit machine and then a man into the dog suit machine, and we get both of these things going on. You can even put something back into itself. So here we've got a dog that we have put into the dog suit machine. So you have to just start to think, what would happen if you put a human suit into the dog suit machine? Well, if we put a human suit into a dog suit machine, then we would end up with, and I don't have a picture of that, you know, that's going to be like the three-piece suit, but it's going to be inside of a dog suit, and then there's no substance to it. But you just have to be very careful about what's on the inside and what's on the outside. And is it going back into itself, or is it going back into a different machine? Okay, now on our previous one, they were both like suit machines, but they're often not even the same kind of machine, and we link them up. So here this is showing probably kind of older for some of you, but an old-fashioned change machine and then an old-fashioned Coke machine. I used to be able to take $1 and go put it in the change machine and get some coins out, and then go put some of the coins into a Coke machine and get a Coca-Cola out. Now, you know, the machines themselves, you're just going to put your card in or the money, and it's going to take more than $1. But when we say, what if f of x is the coin machine, g of x is the soft drink machine, then g of f of x means to take the coins, because remember, f of x gives you coins. Take the coins and put them into the soft drink machine. But x would have been like a dollar bill. A dollar bill was turned into coins, and then the coins were turned into the soft drink. Now, if you actually have a machine that you can put a dollar bill into and get a soft drink out of, you don't have to have coins at all, then it's like you've got a composite there. It's taking care of both things at once. So in algebra, the x function is really just holding the place. You can replace the x with a number or with an entirely different algebra function. So when we're doing composites, we are putting one into the other. Now this f, and it looks like an O, but we really should say f of g of x, or the composition. Okay, you can read it like that too, the composition of f and g. So I can read this from left to right. The composition of f and g of x is equal to f of g of x. So f of g of x. And because f of g of x is easier to say than the composition of f and g, generally I'm just going to say that latter one. But x has to be in the domain of g, because that's what it's getting plugged into. And then g of x has to be in the domain of f. In other words, backing up to this old-fashioned thing, this old Coke machine, you couldn't put $1 in. You had to have coins. So you couldn't put the $1 into this Coke machine, but the $1 would go into the change machine, and then what you get out of this would go into the next one. And that is what it's saying down here at the bottom. X is in the domain of G, $1 goes into the change machine, and then the change you get is what goes into the Coke machine. So how does this really apply to the algebra then? Enough with the suits and the machines. Let's see how it works. All right, so I've just got a page with several examples here. Again, as frustrating as this can be to you, you are going to end up with problems, again, where they give you a couple of functions and then they give you a nice big list of problems that you need to work. So these are all written up at the top. We're going to try to label it down here, and I'm going to rewrite it. F of g of x means f of g of x, and you can see then that g is the inside function. So g has to get plugged into f. So the outside function is f. F tells me 2 times something minus 5. The inside function then is where I'm going to put my g of x. But what is g of x? G of x is x squared minus 3x plus 8. So now that's 2 times g of x minus 5, which is 2x squared minus 6x plus 16. 2 times 8 is 16 minus 5, which is, bring it back to the left here, 2x squared minus 6x plus 11. Now it also says on part A, do g of f of x. Well, g of f of x means f of x is my inside function. So looking at my outside function g, I have something squared, because x is holding a place for something, minus 3 times something plus 8. But now my inside function for both of these little places needs to be f of x. So what is f of x? Well, again, I could have written it something squared minus 3 times something plus 8. And now inside those parentheses, I'm going to put my f of x. F of x is 2x minus 5. Okay, so now I need to clean up to square this. Now you can write out 2x minus 5 times 2x minus 5, but I'm going to use the pattern. I know it happens when you've got something times itself, a binomial times itself. You get the first term squared, multiply the terms and double them. So when I multiply that, I get negative 10. Doubled is negative 20x. Last term squared, so negative 5 squared is positive 25. Then I need to distribute the negative 3, so negative 3 times 2x is negative 6x. Negative 3 times negative 5 is positive 15, and then I have a plus 8 out there. So now I need to combine my like terms. 4x squared. Now looking at the x terms, I have negative 20x minus 6x, so that is negative 26x. Then for my constants, I'll try to put a scribble under them, I have 25 plus 15, that is 40. And 40 plus 8 is 48. So I have plus 48. All right, so those were my two B's for part A. For part B, then, what is it that we can do? Well, for part B, it says f of g of 7. Since this is a number, this actually is a lot more like those machines I was talking about. I can take the 7 and plug it into G and see what I get. And then I can take that answer and plug it into F. Now, I could go ahead and use these composite functions also. So like when I want to do f of g of 7, I could just plug it into this one. So for part B, f of g of 7 is f of g of 7. So now I can just go find out what is g of 7, okay? G of 7 just takes 7 and plugs it into that g function, so it's 7 squared minus 3 times 7 plus 8. Of course, the calculator is going to help you do this pretty quickly and accurately. So that's 49 minus 21 plus 8. 49 minus 21 is 28, and 28 plus 8 is 36. All right, if g of 7 is 36, then f of g of 7 is f of 36. So now I can take 36 and plug it into the f function. So I have 2 times 36 minus 5. Well, 2 times 36 is 72. And then 72 minus 5 is 67. All right, if I want to do g of f of 7, still part of B, g of f of 7, we want to find out what f of 7 is first. So I'm going to take 7 and plug it into that f function. 2 times 7 minus 5. Which is 14 minus 5, which is 9. So that means that g of f of 7 is the same thing as g of 9. All right, so now I need to do 9 squared minus 3 times 9 plus 8. It's going to be 81 minus 27 plus 8. 81 minus 27 is 54, plus 8 is 62. So this one equals 62. 62 is the answer. So you can see, even though they looked very similar at the beginning, f of g of 7 and g of f of 7, they are not the same, okay? You have to use the order that's given. So now these other two are a little bit shorter. So when we do part C, I can do that down here. It's g of 1. Again, first of all, just find out what g of 1 is. So when I plug a 1 into g, I get 1 squared minus 3 times 1 plus 8. Well, that is 1 minus 3 plus 8. 1 minus 3 is negative 2. Negative 2 plus 8 is 6. So then I need to do, well, if g of 1 then is the same thing as g of 6. So now I need to take my 6 squared minus 3 times 6 plus 8. All right, that's 36 minus 18 plus 8. 36 minus 18 is 18, and 18 plus 8 is 26. All right, let's get part D. Part D is f of x. Well, I don't actually have to go figure out what f of x is because it's given to me exactly in the problem. But I have to plug that back into itself. So that means everywhere there is an x, I'm going to replace that x with f of x. So that means it'll be 2 times f of x minus 5. But that, what is f of x? 2x minus 5. And so then I have 2 times 2x minus 5 minus 5. So you can see here it's been plugged back into itself. So now we clean that up and we have 4x minus 10 minus 5, which is 4x minus 15. And that's the answer. We do have to watch out for domain limitations. So here, if we're going to find f of g and then g of f of x, we need to look individually at what those domains are. So when you're dealing with f of x, I know that x minus 2 cannot be 0. And if x minus 2 cannot be 0, then for f of x, I know x cannot equal 2. Now, additionally, over here on g of x is in the denominator, and x cannot be 0. Now, this is not necessarily the only thing we need to look at with domain. We all have to look at their domains individually as well as when we put them together. So when we do f of g of x, that is f of g of x, and I'm going to start with this outside function since I don't actually have a number to plug in, and we'll just say, well, what is f holding a place for? So f is 1 over something minus 2, and the something that I'm plugging in is g of x. Well, since g of x is going into this particular spot, then this is where I know that g of x, just like I was doing the domain for f of x, g of x is cannot equal 2. So now we're going to keep that in mind, and it might not be the finished product, but that's a part of it. We know we can't let g of x equal 2. If g of x cannot equal 2, then I have to consider what makes that happen. That means 5 over x cannot equal 2. And with a little bit of algebra, we find out that that means x cannot equal 5 over 2 or 2.5. So we're going to have to keep this one. We know we can't let x equal 5 over 2 or else g of x would equal 2 and then the whole thing would equal 0 on the denominator, and that would be a problem. But additionally, we're going to go ahead and finish plugging this in and simplifying a bit. So here I get 1 over 5 over x minus 2. Now there's more than one way to simplify this. What I'm about to do you might not be familiar with, but when you have complex fractions, you can multiply each portion of it by what would be a common denominator. Since this is my only small fraction, I can multiply each part of this by what would be the common denominator, which is just x. And then that's going to simplify so that those x's where I had that denominator will cancel, and I end up with x over 5 minus 2x. Okay? Now, the moment I plugged this in right here, I also had to keep in mind when it had 5 over x, right here I need to point out that x cannot equal 0. So I have actually used both of my outer domain limitations. On the outside, x cannot equal 2, and that's where I got this first limitation. But on the inside function, x cannot be 0. So on this one, I have simplified it, but the domain is everything except for these two values. So the domain is negative infinity up to 0, then skip 0 and go to 5 over 2 or 2.5, And then we have to skip over that and go from 5/2 to infinity. So it does certainly get more complicated when we're not dealing with particular values, because we have to watch out for domain, which means I need to look at the originals as well as the composite. Now we still need to do G of F, and so we'll change colors again and see if we can get something else going, and I'm going to squeeze that in there. So if we need to do G of F of X, my outside function is G, and G says 5/something. Well, I know this something cannot be 0, so when I say, okay, I'm going to put f of x here, then I know immediately f of x cannot equal 0. I'm just going to kind of draw a little arrow and say f of x cannot equal 0. But again, if f of x cannot equal 0, we need to look closely at that. Well, f of x is 1/x minus 2, but a fraction never equals 0 unless the numerator equals 0. So although this is true, f of x cannot equal 0, 1/x minus 2 would never equal 0, so this one is not a problem. So I get to go ahead and continue and look at this in more detail. So as we continue, this becomes 5/1/x minus 2. But now I have my next domain limitation, because right here, I know that x minus 2 cannot equal 0, which of course means x cannot equal 2, just like we had in our earlier one. Okay, up at the top where I wrote that in red, f of x, we know that there's a domain limitation there. So x cannot equal 2. Now, when I continue this, I can use this. This is a whole number divided by a fraction, so I can use keep, change, flip sort of idea. We keep the 5, change it to multiply, and flip that fraction over, but 1/x minus 2 just flips to become 5 times x minus 2, which is 5x minus 10. And then our domain, as we write it down, we did have a limitation. Even though I didn't have to worry about the first one, I do know that x cannot equal 2. So I'm going to have to skip over that. So it goes from negative infinity to 2. It goes from negative infinity to 2, skips the 2, so then we union that with 2 to infinity. Remember then, when we're dealing with composites, we need to look at each function's domain and then how that domain changes or adjusts as they get put together. And that can be rather complex. What I'm going to do is maybe I will say it like this. If you can look at something and say, well, what part is on the outside and what's on the inside? This part right here that I'm putting in yellow, this is not the only way to do this type of problem, but I definitely think it's the easiest. That in yellow is the inside. So my inside is right in there. So we're going to make g of x be the inside function. So g of x is equal to 2x minus 3. Now, besides the 2x minus 3, what is left? Well, that's the outside function. So f of x is something raised to the 5th. I really don't need those parentheses, but I do need a placeholder. So rather than the parentheses, what is it we use for a placeholder? The x. So now I just looked at what the inside is and wrote it down. And then essentially for this outer part, I'm saying, and if you take what that is and raise it to the fifth, you'll have it. So let's look at an inside part on this next one. This is a separate problem. The inside part is x plus 3. The inside function is g of x. So let g of x equal x plus 3. All right, then the outside function is what's left, which is the 1 over, and then we've got to raise it to the third, so I need a placeholder for that. So if you'll take this inside function and put it where I have an x for this one, you will suddenly have that function. So to separate them, the easiest way to do that is to think of inner and outer functions. Okay, one more video for us on here. If you have graphs, and they will give you a problem or two with graphs, and you have to find composites. So we'll write everything down on this first one for sure. But this is the same as, well, I guess what we'll do first of all, let's look at this. G of negative 2. You want to go to the G graph and let x be negative 2. So the G graph is this green one. So on this green graph, if I go to where x is negative 2, the y value right here is positive 2. So what that tells me is that g of negative 2 is equal to positive 2 because that's the x value I used and this is the y value I got. So g of negative 2 is positive 2. So then that means this problem becomes f of positive 2. So it's kind of like on the graph part, you just kind of have to restart over and say, okay, I'm going to let the x value be 2, but I want to go to the f function and find out what that y value is. So I go over here to the x value of 2, but the f function is the red one, so that y value is negative 2. So f of 2 is negative 2. So I know it's kind of crazy. We go to the very first x value and then go to the first function to get at the first y. Then let that become the x value for the next function. All right, let's try again. So what is g of 2? Well, we want to go to 2 on the x's and then find out what that equals on the g function, and it gives me 5. Which means I need to find f of 5. What was the y for the g function becomes the input or the x value for the x function. So I go out to 5. 1, 2, 3, 4, 5. Okay, and I want to go up to this f function and find out what that height is, and it looks like it's 4. All right, the next one starts with the f function. So what is f of 2? Well, I can use this. I've already found that work. I don't have to work again. F of 2 is negative 2. So that means now we are finding g of negative 2. And you can do the work again, but I really shouldn't have to. G of negative 2 is equal to 2. All right. What is f of 0? F of 0 is 0. So now we want to find g of 0. So if you use 0 and then you go to the g graph, we get 1. Now here we have g of negative 2 Well, I've already found g of negative 2. It was equal to 2. This one is still the g function, but now I'm putting a 2 in. So what is g of positive 2? Well, I go over to positive 2, go up to the g function, and it looks like that one is 5. Okay, so it's just like taking those dollars to the change machine and then getting the quarters out of that and taking them over to the other machine. You're putting what came out of one into the other one. Okay, and that finishes up our lesson on the composite functions. I hope this helps you out. Please send me any Ask the Instructor questions you have. I answer emails as quickly as I can.